This video covers section 1.5 on what we call Leibniz notation and the power and sum difference rules. These are all rules and notation regarding finding derivatives. So we're going to start learning shortcuts to finding slope of the tangent line formulas rather than having to use our limit definition that we used in section 1.4. So the objectives of this section are to be able to differentiate or find the derivative using both power rule and sum difference rule. Differentiate a constant function or a constant times a function, and then determine points at which the tangent line has a specific slope. All right, so our first part here is understanding what we call Leibniz notation. So when y is a function of x, we also will write the derivative using a different form. So we talked about in section 1.4, we define our derivative to be written using what we call prime notation, f prime of x. And we would write that as, in Leibniz notation, meaning the same thing as f prime of x, we write dy over dx. We would interpret this as the derivative of y with respect to the variable x. So the dy over dx means exactly the same as finding f prime of x. So when you're asked to find f prime or if you're asked to find dy over dx, they mean exactly the same thing. Find the derivative of the function. All right, so our first theorem is theorem for what we call the power rule. For any real number k, the derivative of y with respect to x, if this is our function y, x to the power of k, is found by taking the exponent k and multiplying it by x raised to the k minus 1 power. So the exponent comes down in front and becomes the coefficient, gets multiplied by the function, and then the new exponent is 1 less than what we started with. So if I wanted to find the derivative of each of the following functions, so starting off with y equals f or y equals x to the fifth, then we're going to do y equals x, and then we're going to do y equals x to the negative fourth. So in the last section, when we had to find the derivative, we had to do the limit as h approaches 0 of f of x plus h minus f of x over h and work all that through. So this power rule is the first of many shortcuts you're going to learn to doing the same thing. So for part A, the derivative with respect to x of the function x to the fifth by our power rule is simply the exponent is 5, so that comes down to the front, multiplied by x to 1 less power, so whatever 5 minus 1 is, or in other words, 5x to the fourth. You can skip writing this down if you can do that in your head. Just know that the power is now the coefficient and the new power is 1 smaller, so 5x to the fourth. Derivative with respect to x of just the function x. So the power here isn't written, but it's a 1, right? So 1 is the power, so that comes down to the front. And the new power becomes 1 less. So the original power of 1, subtract 1. So 1 minus 1, however, is 0. So x to the power of 0 is just 1. So 1 times 1 is simply 1. When you have a constant function where, the linear function where the power is 1, the derivative will just be the coefficient only. So whatever the coefficient is, because think about what it means. It means you're finding slope. So if this was the equation that you were given, this is the equation of a line when the power is 1, so the slope is the coefficient of x, 1. All right, derivative with respect to x of x to the negative fourth. So our power rule says bring down the negative 4, make it the coefficient, and then change the power on the x to 1 less. So the x stays here, and then your new power is the negative 4, which is what we had before, subtract 1. So when we simplify that, we get our negative 4 in the front, and our new power is 1 less, meaning negative 4 minus 1 or negative 5. So negative 4x to the negative fifth. All right, a couple more here. Differentiate y equals x to the 15th, y equals x to the negative 7th, and then explain why the derivative of pi squared is 0 and not 2 pi. All right, so power rule for both parts. Derivative with respect to x of x to the k, our power rule says, is k times x to the k minus 1. So y equals x to the 15th. Derivative with respect to x would be 15 x to the 14th. 15 becomes the coefficient. The new power is 1 smaller. Y equals x to the negative 7th. The negative 7 derivative with respect to x. Negative 7 is the coefficient. The new power of x is 1 less. So negative 7 minus 1 is negative 8. So negative 7x to the negative 8th. And then the reason that when you take pi squared and try to find the derivative, you should get 0 and not 2 pi is because pi is not a variable, right? You're differentiating your function with respect to x, meaning that the variable x. So pi is just a constant. So pi squared is just a constant. So that's just a number. Okay? The derivative of any constant is 0. Okay, so that's just a rule. The derivative with respect to x of a constant is always going to equal 0. And since pi is a constant, pi squared is a constant, so the derivative is simply 0. All right, differentiate. Y equals the square root of x and y equals x to the 0.7. Okay, on this first one, we have to rewrite the square root of x using exponents. So the derivative with respect to x of the square root of x will be the derivative with respect to x. We're going to rewrite this as x to the power of a half. Then to take the derivative, we use our power rule. The 1/2 is the exponent. It comes down in front as the coefficient. Our new power is going to be 1/2 minus 1. It's going to be 1 less. So 1/2 subtract 1 is negative a half. So we'll get 1/2 in front, x to the negative 1/2, or a negative exponent means we can move that x down to the denominator. So this x moves down to the denominator where the 2 is and turns into a positive 1/2 power. And again, the 1/2 power can convert back to being a square root. So we get 1 on top, and then the 2 is on the bottom, and this got moved down as x to the 1/2 or the square root of x in the denominator. X to the 0.7 power. Derivative rule says bring down the 0.7, make the new power 0.7 minus 1. So we get 0.7, and then x to the power of 0.7 minus 1 is negative 0.3. Oops. Okay. You could bring that down to the denominator as put the x on the bottom as a positive 0.3 if you'd like. They just didn't do that here. All right, here's the rule we talked about with the derivative of a constant being 0. So the derivative of any constant function is always equal to 0. And again, you can understand that by thinking about derivative means slope. So if you've got a function y equals a constant, it's a horizontal line. The slope of any horizontal line is 0 at every single point. All right, the derivative of a constant times a function is the constant times the derivative of the function. So in other words, if you have a constant multiplied by a function, you can factor the constant out, differentiate the function, and just multiply by the c. All right, so if I have 7x to the 4th, negative 9x, and 1/5 or 1 over 5x squared, we're going to find our derivatives. So the derivative with respect to x of 7x to the 4th, it's like you can think of it as the 7 being factored out to the front. So it's the same as 7 times the derivative of x to the 4th. So that derivative by the power rule would be 4x to the 4 minus 1, or this would become 4x cubed, but it was multiplied by 7. So the 4 and the 7 multiply together and give you 28x cubed. And really, you don't have to show all of these little steps. It's just bringing down the 4 to the front and multiplying it by 7. That's a 28. And then x to the power of 1 less than 4. So 4 comes down and becomes 28 coefficient. And then this becomes x to the 3rd. All right, here, this we can think of as being a linear function, right? This would be y equals negative 9x. That's the graph of a line. So our derivative should just be negative 9. Right, we can see it by using our rules. Bring out the negative 9, then just differentiate x. Again, this power is a 1, so the 1 would come down to the front. The new power would be 1 minus 1. 1 minus 1 is 0. X to the 0 is 1 times negative 9 is simply negative 9. So again, any x to the power of 1, its derivative is just the coefficient. All right, next we're going to do 1 over 5x squared. So that 1/5 can factor out to the front. That's a constant, so we can write it as 1/5 times the derivative of the 1 over x squared, if you'd like to do that first. Then we're going to have to rewrite this. We can't take the derivative within a denominator, so you're going to have to bring this up to the top and make it a negative exponent in order to utilize your power rule. So any variables that are in the denominator, you got to move them to the numerator before you can apply your power rule. So bring it up, makes it a negative power. We haven't done any derivatives yet. Notice our derivative notation is still sitting here. We just rewrote our function. So now we apply our power rule. So the -2 comes down. The new power is -2 minus 1. So we end up with, we've got 1/5 times -2, which is -2/5, x to the power. This new power then would be -3. Or, again, the -3 exponent means you can move the x down to the denominator with the 5, and when you move it down, you change the exponent to being a +3. So we end up with the -2, the negative in front and the 2, and then the 5 on the bottom, and then this moved down to the bottom to make the power a positive number. All right, so let's try a few more here. Part A, y equals 10x to the 9th. Part B, y equals pi x to the 3rd, and part C, y equals 2 over 3x to the 4th. All right, so this first one, derivative of y with respect to x. The 9 will come down to the front, so the 9 will be multiplied by that constant 10. The new power is going to be 9 minus 1. So you're going to get 90 x to the 8th. On part B, the 3 will come down to the front, multiplied by pi. The new power will be 3 minus 1. So the constant pi in front behaves just like a constant of 10 or whatever. So 3 pi x to the 2nd. This one we're going to have to bring up that denominator variable term. So the 2/3, that's just the coefficient. The 3 stays put, it's just a number, but the x has to move up, and that changes the exponent to being a negative. Right? Then you use your power rule. You bring down the -4 to the front. It's going to get multiplied by that 2/3, and the new power is going to be -4 minus 1. So -4 multiplied by that 2/3 is -8/3, and then the -4 minus 1 makes the new power -5. And then you could shift that x to the -5th, put the x down in the denominator, makes the power +5. So you get -8 on top, 3 on bottom, and then that x on the bottom would then have a +5th power if you move it down. So if it's on the bottom to begin with, you have to move it up, then apply your derivative power rule. Then if you still have a negative exponent, then you can move it back down. All right, sum and difference policies or rules on derivatives work the same as limits. So if I had to differentiate the sum of two functions, you can just find the derivative of each term separately. Same with differences. Okay, make a note here in your mind here that this does not work for products. If you're multiplying two functions together and want to find the derivative, you can't just find the derivative of each function and multiply together. We'll learn those rules later. But if you're adding or subtracting, you can differentiate through your parentheses or do it term by term. All right, so find the derivative of 5x cubed minus 7, and then we'll find the derivative of 24x minus the square root of x plus 5 over x. All right, so this first one means we can find the derivative of 5x cubed and then minus the derivative of 7, right, by our difference policy. All right, so again, you can factor the 5 out if you want, then just differentiate x cubed. The derivative of a constant will be 0. And then this derivative will be 3x to the 2nd, but then it's multiplied by the 5. So the 5 and the 3 will get multiplied. My new power will be 1 less than 3. So we should just get 15x squared. You don't have to write all this out. You get to a point where you can just look at that and go, okay, 3 comes down, you get 15. My new power is a 2. So 15x to the 2nd minus, and then that derivative is 0, which is 15x to the 2nd. All right, part B, we've got 24x minus the derivative of the square root of x plus the derivative of the 5 over x. We're going to go term by term. All right, so this first one, 24 times the derivative of x We'll change this to the x to the 1/2. Here we'll pull out the 5 and then differentiate the x, and they brought this x up to the top as a -1. I would recommend writing this as the 1/2 power first and writing this up here as an x to the -1st power, definitely. But as far as factoring out the constants, you can, if you want to write that down, fine. If not, you don't necessarily have to. All right, so the derivative of x was just 1, right? Because the coefficient is 1 of the linear function. So we got the 24 in the front, though, so it's going to be 24 times 1. Here, the 1/2 comes down to the front. 1/2 minus 1 becomes the new exponent. And here, the -1 comes down to the front as the coefficient, and the new exponent is -1 minus 1. So we end up getting 1 minus 1 is 0, so x to the 0 is 1 times 24, that's 24. 1/2 minus 1 is -1/2, so we get 1/2 x to the -1/2, but again, that means the x moves to the bottom as a positive 1/2, and the 1/2 power gets rewritten as a square root. And then here, these multiply together and give you -5. And then -1 minus 1 is -2. So we end up with the -5, but then we can bring the x down to the bottom and make that power a +2. All right, so let's try this one. Here you might want to pause the video and try this one on your own first, and then pick it back up and check your answer. We want to differentiate y equals 3x to the 5th plus 2 times the cubed root of x plus 1 over 3x squared plus the square root of 5. All right, so our first step here, I would suggest writing the cubed root as x to the 1/3. Rewriting this term as 1/3, but then bringing this up as x to the -2nd. And then just keep in mind that this is a constant. It's a square root, but the number underneath is a number. It's not a variable. So this is just like differentiating any constant. All right, so our derivative of this function. First, we're going to rewrite it. So we're going to take the derivative of 3x to the 5th. The derivative of 2, we're going to write this as x to the 1/3. The derivative of 1/3, we're going to write this as x to the -2, and then the derivative of the square root of 5. All right, so our first one here, 5 will come down in front. You get 5 multiplied by the 3, x to the new power is 5 minus 1. Here, the 1/3 will come down in the front, so when I bring down the 1/3, I get 2/3 x, and then 1/3 minus 1 is the new power. In the next term, we're going to bring down the 2, so we're going to get -2/3, the new power, -2 minus 1. And then that last term, because there's no x's involved, it's just a constant, its derivative is 0. And then we clean it up. Will give us 15x to the 4th plus 2/3. This will be x to the -2/3 plus, or I'm sorry, -2/3 x to the -3rd. And then your 0 can be dropped. And then we're going to clean up these exponents here. So we got a 15x to the 4th plus 2 over 3. This x is going to move to the denominator as a positive 2/3. And then they converted it back to a radical. So the positive 2/3 power means the cubed root of x squared in radical form. And then this one, just simply the x moves to the denominator as a positive 3rd power. And that's the answer. So a lot of little algebra things here, remembering how to handle negative exponents, remember how to handle radicals in exponent form, and just being careful and watching your signs. All right, here we want to find the points on the graph of f of x equals -x cubed plus 6x squared, which the tangent line is horizontal. All right, so we're kind of trying to tie some concepts together here. Tangent line, we've just spent a couple sections talking about that the slope of the tangent line means the derivative. Okay, so we're going to have to remember that. And then if I want the tangent line to be horizontal, the line is horizontal, its slope is 0. All right, so that the derivative is the slope of the tangent line, and the slope of a horizontal line is 0. So when they're asking us to find the points on which on a graph for which the tangent line is horizontal, we need to find the points on the graph for which the derivative, which is the slope of the tangent line, is equal to 0. All right, so here's my function. First, we're going to find its derivative. So our power rule says the negatives can sit in the front. We're going to bring down the 3 and make the new power 1 less. 3 minus 1. Here we're going to bring down the 2. Just leave the 6 there. Bring the 2 down and make the new power 2 minus 1. Okay, or you can just look at this and go, okay, negative stays here. You get 3 in front. 1 less than 3 is 2, so negative 3x squared. Bring down the 2, that gives me 12. 1 less power on x would make it x to the first. So negative 3x squared plus 12x. All right, so that's my derivative. Now we're going to set the derivative equal to 0. So negative 3x squared plus 12x equals 0. And we're going to solve. So we can solve this by factoring. We can factor out the negative 3x. That leaves x minus 4. And then we can set each factor equal to 0. And solve each equation. So we get x equals 0 and x equals 4. So we have 2 values. Now remember, our question says find the points. So we have at this point just found our x values. So there's 2 points, it looks like, where there's a slope of 0. But we only have identified the x's. So to find the corresponding y values for those x's, we're going to plug those back into our original function. So our value of x being 0, we're going to find its y values. We're going to find f of 0. Plugging that back into the original function, looks like this, and that gives me a 0. The other x value we found was 4. Plugging that back into the original function, negative 4 cubed plus 6 times 4 squared, gives me 32. So the tangent line to this function's graph is horizontal at the ordered pair 0, 0, when x is 0, y is 0, and at the point 4, 32. So here's an illustration of that. Here's the graph of the function f. Here's the ordered pair 0, 0. Notice if I drew a tangent line right here, it's flat, right, meaning horizontal. Here's the point 4, 32, right here. If I drew a tangent line, it's horizontal. Notice this is a point where the graph hits like a bottom of a hill, like a low point. And then over here, it hits a high point. It's coming up, and then it turned around to come down. So we'll talk about all those relationships later on, but that's important to notice. All right, this last example, find the equation of the tangent line to that function at the point 1, 5. So if I want the equation of a tangent line, we first need to find the slope of the tangent line. All right, so our slope, f prime, our slope equation is right here. F prime of x equals negative 3x squared plus 12x. So when I plug in 1, I get negative 3 times 1 squared plus 12 times 1, which is negative 3 plus 12, which is 9. So we find the derivative using our power rule, or whatever rule we can apply. We plug in the x value of our point. That's why I plugged in a 1, because the x value of the ordered pair was 1. That gives me the slope of the tangent line. So the slope of the tangent line at 1, 5 would be the 9. Now we're going to write the equation of the tangent line using our point slope formula. You could also use slope intercept, plug in x, y, m, solve for b. That's fine. You'll get negative 4 if you do that. I'm just using point slope instead. So the point slope, y minus y1 equals m, x minus x1. So y minus the 5 equals my slope was 9 times x minus the 1. Distributing 9 gives me 9x minus 9. Adding 5 to the other side gives me y equals 9x minus 9 plus the 5. And then that cleans up to be y equals 9x minus 4. If you did the y equals mx plus b version, y would be 5, m would be 9, x would be 1. You would solve for b, and you should get negative 4 as your b value. And then you could get the same answer. So the equation of the tangent line to this original function at the point 1, 5 is y equals 9x minus 4. All right, so a summary of what we've talked about here. Common forms for notation for derivative. F prime was how we first started. Sometimes if the function's given as y, we would write y prime. So that's prime notation. Leibniz notation was dy over dx. Sometimes you'll see it as d over dx of the function f. So depending on if they're defining the function using y or f of x. But all those things mean finding a derivative. The power rule, derivative with respect to x of x raised to the power k is k times x to the k minus 1. The derivative of a constant, 0, always, no matter what. The derivative of a constant times a function is the constant times the derivative. Sorry if you heard my dog barking. We'll start over here. The derivative of a constant times a function is the constant times the derivative of the function. The derivative of a sum or difference means you can differentiate each term, right, through your plus or minus sign. Okay, so that's just kind of a summary of all the rules, okay, and then the examples that we did to apply them within this section. And that is the end of section 1.5.